Good evening, ladies and gentlemen. Wildfires are a serious threat to the lives and property of everyone in the United States, most especially here in California. The combination of drought, warmer temperatures, plus the high winds alongside the excess of dried vegetation fuels here has made fire seasons progressively worse over the past 50 years. What would be the most prone to these menacing conflagrations, you may ask? Timber residential structures. That is why we should investigate ASTM E2957, the standard test method for resistance to wildfire penetration of eaves, soffits, and other projections. I, Paul Ian J. Kabasag, will be your presenter today, so without further ado, let's begin. I would like to start out by motivating the susceptibilities of residential buildings to exterior wildfire exposures. The video you are about to watch is a large-scale test from the Insurance Institute of Business Home Safety Research Laboratory in South Carolina. The simulation offers a representative wildfire event with a firebrand ember generation to test how a typical residential home holds up against a wildfire condition. The four structure components that you would see that must be assessed for fire resistance are roof eaves or projections, external wall finishes, vents, and exterior windows. As you can see, the first object that ignites are the asphalt shingle roofing material. What you see here is spotting that can cause accumulation of leaves along gutters and roof eaves to ignite. The ignition of wall finishes can produce high concentration of soot particles that may increase fire intensity due to radiation. Subsequently, you will see the exterior wildfire propagate into the interior spaces via vents and windows. Due to the sake of time, the test method that I will only delineate will be related to the roof eaves and projections. The topics of interest will be historical background, test method, code reference, and thermal fundamental analysis. The slides will show a comprehensive detail of the test standard with the intent of giving you guys a complete description. The color coding of the slides demonstrate that the red fonts refer to code references or lecture notes, the green fonts refer to terminology, and the blue fonts refer to phrase emphasis. For historical background, let's discuss the different editions of the test method and standard test alterations throughout the years. So far, this test method has only been around for 2 years, with its first publication back in August 2015. The second publication came about actually just this month. So far, there's only been 4 standard updates, so not that extensive. First, if you guys can peruse through section 1, paragraph 1.10, the previous edition placed this provision as a floating entity above page 1, whereas the current edition had appended the provision to section 1. The purpose of the change is for administrative means to organize standard testing caveats. Second, if you guys can turn to section 11, paragraph 11.2, the previous edition did not control the boundary condition of the location of the roof eaves or floor projections relative to the testing apparatus. The current edition now provides an added description of how to orient the testing specimen relative to the apparatus. The purpose of the update is to control the boundary condition of the test to strictly specify the vertical distance between the testing specimen and the ignition source burner. A more stringent provision is now imposed to control the horizontal distance between the wall assembly and the burner to prevent flame impingement through the wall and reduce flame spread vertically via direct flame conduction, which may affect the acceptance of performance criteria of the tests. Third, if you guys can read through the section 12, paragraph 12.1.4, the only change is updating the period to a comma. Needless to say, this is just for punctuation consistency. Fourth, the previous edition addressed providing in the test report the details and materials of only the testing specimen. Now the provision addresses providing in the report the same information for both the testing specimen and apparatus. The purpose of the change is to provide a method to confirm testing conformance of dimensions and assembly. Now we will delve into the development of the test standard. Bear in mind that I will only highlight sections of the test here and detail the steps of the procedure in the test method portion. To prevent flame ignition and induce wildfire resistance, the State Fire Marshal and International Wildland Urban Interface Code recommends establishing a performance criteria for building materials used on exteriors of buildings. Specifically, the goal of E2957 addresses the issue of direct flame contact with roof eaves and other floor projections. The motivation of the standard was to address flame penetration problems with combustible and non-combustible wall finishes. The fire size and exposure time from the pilot source was developed by the Forest Product Fire Research Laboratory at UC Berkeley for experiments on ignition of ornamental plants and combustible exterior cladding adjacent to roof and floor projections. The observation period started with 60 minutes where visual cues of flame penetration began to emerge with common failure points at joints and knots of the structure components. Further testing at Western Fire Center and University of California Cooperative Extension by SFM spearheaded the research of determining appropriate fire size, exposure time, ignition source geometry, and wall assembly. Finally, based on the aforementioned test development program, a standard test was created that eventually got adopted in the California Building Code and State Fire Marshal Standard. Knowing how it was created, now let's talk about how to perform it. What you see here are the 2 testing models provided by the test method, one being the roof eave apparatus and the second being the floor projection apparatus. The main components are the wall assembly, the holding fixture with the shield, and the ignition source which is a combination of the burner and the metal stand. The models are identical except the difference in testing specimens as highlighted. How the test method is applied is to follow a 15-step procedure for both of these. Initially, the first 4 steps outline prepping the models. Next, once the burner is turned on to reach the heat release rate of 300 kilowatts, the wall assembly and test specimen are mounted onto the holding fixture. Then at the onset of igniting the burner, perform the 2-stage process of a 10-minute flame exposure period and a 30-minute observation period. The test is performed in triplicates to reduce the amount of variability of performance. Afterwards, the test report and results are fabricated for documentation. Finally, the test results are assessed if it conforms with the standard performance criteria that requires at least one replicate to meet all three criteria shown here. Now that you guys have the full gamut of the test standard, why don't we assay the code references? Primarily, the code applies to any new building construction after the July 1st, 2008 that reside within a wildfire-prone zone area dictated by a map provided by the Board of Forestry and Fire Protection. Here are some definitions that apply for your interests. To summarize the organization of how the codes are applied, is that the governing document is the California Building Code that references 5 resistance options of either specifying non-combustible material, ignition-resistant material, append a layer of type X gypsum, extend fire rating of the wall assembly, and conform to either one or two testing standards of SFM 127A3 or ASTM E2957. If you remember from the introduction video of the vulnerabilities of a structure against wildfires, all the components I mentioned that needed fire resistance are clearly outlined in the SFM standards as shown here. 1, 2, 3, 4, 4A, and 5. However, for our own purposes, we are only focusing on SFM 127A3, which is the fire resistance of horizontal undersides of roof eaves and floor projections. In comparing the two fire resistance testing standards, they are quite similar with 3 exceptions: how the testing specimens are prepared, how the burner is positioned, and how the performance criteria are accepted. The main difference is that SFM requires all 3 replicates to meet all 3 criteria, and if one fails, 3 additional replicates must be performed and meet all 3 criteria as well. Whereas, if you remember, E2957 only requires at least 1 replicate to meet all 3 criteria. Lastly, the NFPA 286 standard is referenced here for the testing standard to show where the ignition source burner position provisions originated from. Now, being well versed in the codes, let's step it back a notch and figure out the physics behind the code. I will probably only cover the main concepts and have anyone that's interested read through the others. So first, what's the relation of heat transfer and wildfires? Exterior wildfire exposure transfers heat to adjacent structures via conduction, convection, and radiation. Conduction is a transfer of energy from the particles with higher kinetic energy to lower kinetic energy as modeled by Fourier's law. In nature, this can be observed as a direct contact from a wildfire short-term flame to a combustible roof eave or soffit or flammable vegetation fuels along gutters, raising the temperature above the characteristic temperature leading to ignition. Pertaining to the test method, the holding fixture and burner position were oriented properly in order to prevent conduction not accounted for the scope of the test. Convection is a transfer of energy to a moving fluid driven by imposed fluid motion or buoyancy that is modeled by Newton's law of cooling. In nature, this can be observed primarily in the fire origin in the forest floor, causing hot air to rise and cooler air to descend, leading to a convection current to form that lead to pilot ignition of leaves and branches of shrubs and trees above the fire. Forced convection dominates in high wind areas where floating firebrands are carried out to unburned areas ahead of the fire front that can result in spotting that causes rapid flame spread, as was shown in the video. In relation to the test method, the test room is situated to account for air velocities to emulate wind effects and unlimited air supply to emulate exterior conditions. Radiation is a transfer of energy through electromagnetic waves that is modeled by Stefan Boltzmann law. In nature, this can be observed in one of two ways. First, excessive radiant heat from large solid fuels can ignite neighboring structures. And second, smoke accumulation can induce radiation from soot to unburnt fuels. Pertinent to the test method, the amount of soot particles that can be produced from a diffusion flame that typically undergo incomplete combustion was controlled by removing products of combustion via an exhaust hood system. Second, how does flame spread apply in wildfires? Flame spread is a diffusion flame that transfers heat through solid surfaces and the process of a moving flame within the vicinity of a pyrolyzing region on the surface of a solid or liquid that acts as a fuel source. The mechanics occurs when the total heat flux transfers flame from a pyrolyzing layer to a heated layer at which the surface temperature of that layer reaches ignition temperature as the mass of the layer decreases that causes flame to spread. This phenomenon is prevalent in wildfires because wind-driven flame spread can have heated layers as wide as 30 feet or longer. In nature, after structural components such as eaves and soffits have been ignited, the flames can propagate by penetrating through the interior spaces via seams or joint openings. On another note, combustible roof finishes can become the heated layers of a pyrolyzing material near the base of the wall and wall cladding. Flame propagation can be affected depending on the geometrical orientation or trench effect. When a solid is oriented vertically, flames tend to spread more rapidly because the boundary layer is closer to the surface. There will be more radiation back to the surface. Whereas when a solid is oriented horizontally, flames tend to spread slowly because the boundary layer is farther from the surface, where energy is less applied to the non-decomposed material. The trench or Coanda effect can have walls deflecting hot air gases directly to the adjacent objects to increase heat flux and flame propagation. Pertaining to the test method, there is a predefined dimension between the gas diffusion burner and the wall assembly in order to prevent unaccounted flame spread that may occur due to the vertical orientation of the wall. On the same note, the inclined orientation of the roof eaves demonstrate that it will have a greater amount of flame spread than the horizontal orientation of the floor projections. Also, the side shields of the holding fixture can deflect the hot gases up to the test specimen, creating a trench effect that would decrease the amount of ignition time and increase the heat flux and flame spread. Third, does applying fire retardants to the roof eaves and floor projections affect fire dynamics? Yes, of course. Heat release rate is the production rate of toxic combustion products. This characterizes the design fire that accounts for the fuel packages of an area and constitutes fire growth rate and peak heat release rate. The values selected for the test method were according to the fuel package primarily found in proximity to roof eaves and floor projections. The addition of ignition-resistant material or fire retardants allows greater formation of char than tar products, which would reduce the heat of combustion of the pyrolysites that in turn reduces flame generated on the pyrolyzing layer and flame spread to the heated layers. In nature, if the material on horizontal underside of the roof, eaves, soffits, and projections are specified as ignition resistant, then it would have lesser flame production and less likely to propagate flames into the interior spaces. For the test method, an alternative is to have an untreated material specified without fire retardants to resist a wildfire, but ensure that the assembly meets the performance criteria per standard. Let's conclude with when you would and when you would not apply E2957. First, you would apply E2957 if you have an eave overhang or any other floor projection that need to resist exterior wildfire exposures that originate from the bottom, but you would not apply E2957 if the wildfire was coming in from the sides or the top, as was shown in the introduction video. Knowing the end-use construction of the residential structure allows the user to modify the details of the test specimen and testing assembly in order to have a representative performance result. Second, you would apply E2957 if the flame ignited the roof eave or floor projection directly, but you would not apply E2957 if the wildfire ignited the wall finishes first and have the flame propagate to the overhangs. This type of fire scenario would probably be a combination of performing E2707 for the fire resistance of the building envelope and E2957 for the fire resistance for the overhangs. Third, you would apply E2957 if the flame ignited the roof eave or floor projections when exposed to an exterior fire, but you would not apply E2957 if fire originated from the interior spaces. Here, you would have to consult NFPA 286 for guidance on fire development from inside the building. With that said, thank you very much, and please let me know if you have any questions in the forum. You guys have a good night.